In this video, I will address three questions. First, what is solar constant? Second, do we have enough solar energy available on the Earth's surface to meet the energy requirement of entire humanity? And the third one, what all the energy technologies do we have to harness this energy? In this case, there is Earth. Earth is revolving around the sun. Okay, the Earth is revolving around the sun. And the Earth, we know that the Earth revolves around the sun in an elliptical orbit. Okay, but the the eccentricity of this ellipse is very small, right? And the sun is actually at one of the foci. Obviously, in an ellipse, you will have got two foci. One foci is here, S1. Another foci is here, S2. So, sun is at one of the foci of this elliptical orbit. Right? So this is how the earth revolves around the sun. And therefore, one thing which is embedded in this whole discussion is that since the earth is not moving in a perfect circular path, the distance between the earth and the sun keeps changing. If the earth is here, its distance would be smaller than when the earth is here, right? We will see here. This is sun, this is earth, right? And let's see. Let's see in the mean distance as the distance between the sun and the earth is not fixed. We will take here the mean distance, right? So the mean distance between the sun and earth we called 1 astronomical unit, right? And its value is 150 into 10 to the power 6 kilometer, or we also call it 150 million kilometer. 10 to the power 6 is million, right? The sun diameter is 1.39 million kilometer. The earth diameter is 12,742 kilometer. Right? Now there are so many data, sun diameter, earth diameter, mean distance between the sun and the earth. So to give all these data a perspective, let's find how they are related. So the ratio of the sun diameter to the earth diameter is 109. It means the sun is 109 times bigger than earth, right? Second, the distance between the sun and the earth to the diameter of the sun is 108. This ratio is 108. What does it mean? That we can put side by side 108 suns between sun and the earth. We can accommodate 108 suns, right? So this gives us a better perspective to understand the distance between the sun and the earth and the geometry of the sun and the earth, right? Now, I discussed earlier that the distance between the sun and the earth is not fixed. It is changing because the earth is revolving around the sun in an elliptic orbit and the sun is at one of the foci, right? So the nearest point to the sun on the orbit is called perihelion, and it occurs on January 5, right? And as the earth moves, so it reaches on the other extreme when the sun and the earth distance is maximum, and we call it aphelion. This point on the orbit which is at the farthest distance from the sun is called aphelion, and this occurs on July 5, right? And we discussed earlier that the mean distance between the sun and earth is called 1 astronomical unit. In short, we call it 1 AU, right? And therefore, if I have to express the sun and earth distance at aphelion and perihelion, so at aphelion it is 1.02 AU, and at perihelion the earth is at 0.98 AU. So this gives us a fairly good idea that how small eccentricity is of this Earth's orbit around the Sun, and this eccentricity actually comes out to be very small, 0.01671. So that's why we can say that the Earth moves almost in a circular orbit around the Sun, but not exactly a circular orbit. It's an elliptical orbit, but with very small eccentricity. Now we will discuss here about solar constant, which was our first question which I initially raised, that what is solar constant. So we will discuss here. We saw that the mean distance between the sun and the earth is 150 million kilometer, right? And the sun emits energy, and it emits 380 iota watts. You see YW here shown. This one, sorry, this one, 380 iota watt. Iota watt means 10 to the power 24 watts. And this energy which sun emits, this is not energy, this is energy per unit time. It's watt, so it's per unit time. Every second sun is emitting 380 into 10 power 24 joules of energy. And this energy spreads spherically from the sun everywhere, right? This is a spherical front which we see. This is a spherical front, and this spherical front keeps growing until it reaches Earth. So, uh, so the energy which sun has emitted is spreading over a sphere, over the surface of a sphere, and until it reaches near the Earth. So it has spread over a very large sphere when it has reached the Earth, right? So if we have to find what is this solar radiation or solar energy which is reaching Earth, mm, per unit area, that is, we want to find solar flux, and this we will call solar constant, GSC. GSC stands for solar constant. So we will determine it. So its value should come out. The solar radiation which is coming over this spherical front, right? The solar radiation at this spherical front, and the area of this spherical front. It's a sphere. So this is, the sun is here, and the sphere is here. So a sphere surface is here. So the radius of this sphere is 150 million kilometer. So the surface area, we know that, of a sphere is 4 pi r square. R stands for radius. So here r is d. So we have written 4 pi d square. So if we divide 380 iota watt by 4 pi d square, it comes out to be 1344 watt per meter square. This quantity is called solar constant, right? However, the value of the solar constant which we just calculated is a calculated one, right? But it has been measured by physical meteorological observatory in Davos, and the value of the solar constant comes out to be 1361 with an uncertainty of plus minus 0.4 watts per meter square. So this is a more accurate value of solar constant. So we understand that what is solar constant? Solar constant is the solar radiation, okay, received by the earth per unit area, okay. But you see, this is the radiation received outside of the earth's atmosphere, right? Because this is not the radiation which we are receiving on the land. On the land, this radiation gets affected by the earth's atmosphere, which we'll see ahead in our discussion, right? So, so just to sum up, that the measured value of the solar constant by Physical Meteorological Observatory Davos is 1361 plus minus 0.4 watts per meter square, right? Uh, one thing, Physical Meteorological Observatory Davos, we also call it World Radiation Center. We know that Davos is in Switzerland, right? So, so they keep updating this value of solar constant with more and more precision, right? So the currently measured value is 1361 with the uncertainty of plus minus 0.4 watt per meter square. So we can roughly take the value as 1361, right? Watts per meter square as the solar constant. So one thing we must keep in mind that this value of the solar constant is measured by assuming that the earth is at the mean distance from the sun, right? So we saw earlier that the spherical front which the area of the spherical front which I have taken is corresponding to the distance 150 million kilometer, which is the mean distance between the sun and the earth, right? If the earth is at the perihelion, this value will becomes 1.2 times more, and if it is at aphelion, it will become 0.98 times of this, which we saw earlier. So now as the sun earth distance varies, the value of solar constant varies by plus minus 3.3%. So for any exact day where we if we have to find the value of solar constant, because the sun is moving, because the earth is moving on an elliptical orbit, so its value is changing from the minimum value at perihelion to maximum value at aphelion. So between these two extremes, how the solar constant is varying, that we can calculate using this formula, which is G equal to GSC 1 plus minus 0.33 cos 2 pi n, 2 pi n divided by 365. N here represents the day number. Like January 1 will be called n will be 1 for January 1. For February 1, for February 1, n will be 31 days of January plus first day of February. 31 plus 1, it will be 32. N will be 32. So if I put the value of n, I will get the exact value of the solar constant for that particular day, right? So we won't call it solar constant. Solar constant is called whenever we measure the value of solar radiation outside the Earth's atmosphere on at the mean distance. Rest all are just called solar radiation, right? So the solar radiation on any nth day will be given by this formula, right? Now let's calculate how much energy do we receive on the Earth's surface, right? So we saw that uh, we receive uh, uh, a heat, yes, a radiation flux, solar radiation flux, which is given by GSC, right? GSC stands for solar constant. Now, if we multiply this value of GSC by the projected area of the Earth, because this is what the radiation is coming on the surface of the Earth from the sun. Sun is one on the one side of the Earth. So if the we are seeing from this side, if we are seeing from this side, this is the eye. If we are seeing from this side, this is the human eye. This we are seeing. So we will see Earth as a circle. Okay, we will see its projection as a circle. So if we multiply GSC by the area, surface area of this, by this circle, by the area of this circle, which will be nothing but pi dE square by 4, right? dE is the diameter of the Earth. So we won't take the surface area of a sphere, rather we will take the area of a circle, because this is the projected radiation of the sun, which is coming on the earth. So here when we calculate the value, it comes out to be GSC multiplied by the area of this circle, whose diameter is same as the diameter of the earth. The value comes out to be 1.8 into 10 to the power 14 kilowatt, right? So now, as I told that solar constant, or the which we calculated just now, we calculated the radiation coming outside the Earth's atmosphere. We have not taken the various factors which affect the radiation which comes on the surface of the Earth. These effects are because of the atmosphere, because of the various dust particles, clouds, etc. in the atmosphere. So this is the Earth's surface, and this is the Earth's atmosphere. The we just calculated the solar radiation which is coming, which is GSC at the mean Earth distance. This is the GSC coming. As 40% of this GSC, as it enters on the surface of the Earth, gets reflected or absorbed, means gets lost. It does not reach up to the surface of the Earth, and this is because of the presence of, it gets absorbed by the clouds which are present in the atmosphere, or they get scattered by dust particles. Some get absorbed by the ozone layer. So Q dash Earth, which has been shown here, is the actual amount of watts per meter square reaching on the surface of the Earth, right? So 40% gets reflected. So how much is actually reaching? It will be 60%, remaining 60% of the Q Earth, which is reaching out at the outside of the atmosphere. 40% is getting reflected, so 60% is reaching on the Earth's surface, which comes out to be 1.08 into 10 to the power 14 kilowatt. So if we do this calculation on an annual basis, this is what is the kilowatt coming, right? So if we multiply it over the entire course of a year, over the entire duration of a year, which corresponds to 8760 hour. In a year, we have got 8760 hour. So if we multiply it with 8760 hour, we will get the total amount of energy which the earth receive on annual basis, right? So it receives uh, this much exajoule. EJ means exajoule. Exajoule is 10 to the power 18 joule. 10 to the power 18 we call exa, exa, right? And let's see how much is the world energy consumption. So world's total primary energy consumption is only 450 exajoule EJ. So if we do this, the comparison of these two values, the total energy which is coming on annual basis on the surface of the earth, and the total world energy consumption, if we take a ratio of the two, it comes out to be 7500, which is way much more than our requirement. So so annually our earth surface is receiving 7500 times more energy than the current world energy consumption, right? So we must, and we should tap this energy. This becomes particularly in this era of global warming and extreme weather which we are observing. We must get rid of all the fossil fuels, etc. Because as per estimate of 2019, uh, there was 490 exajoule, 2490 exajoule, 490 exajoule of fossil energy were generated by the world by just burning fossil fuel. So you must we must understand that this much of burning of fossil fuel must have harmed our atmosphere drastically. So we must tap this solar energy and other renewable forms of energy, right? So we make our earth safer, much more a safer place. Okay. So to tap this solar energy, we are having so many solar energy technologies. So broadly, we can classify solar energy technologies into two parts: solar thermal and solar photovoltaic. So using these two technologies, we can tap this solar energy for the welfare of the humanity, or for the required to meet the requirements of the humanity, and at the same time to make this earth a better place to live by cutting down the consumption of fossil fuels. So what happens broadly in solar thermal technology and solar photovoltaic technology? So in solar thermal technologies, we receive solar energy, right? And we produce heat, right? We produce heat. And in solar photovoltaic technology, we receive solar energy and we directly produce electricity. So these are the two ways, broadly two ways to utilize solar energy. So here in the subsequent discussions, I will only focus on solar thermal technologies, right? So let's see all the solar thermal technologies we have. So broadly, we have got two types of solar thermal technologies: non-concentrating and concentrating. Non-concentrating means we are just receiving solar energy and without any increase in its intensity or flux, we are utilizing it directly, right? And the other one is the concentrating. Concentrating helps us to achieve higher flux at a point. We saw that we are receiving 1361 watts per meter square, which was the solar constant, which we just saw, 1361, right? So but by the time it reaches the earth's surface, it further reduces. So we have got enough solar energy, but it is distributed over a very wide land area. So as a result of this, in this heat flux which is coming from the sun is not very much useful to produce a workable power plant which can produce electricity for our requirement. So we use concentrating solar thermal technologies which focus sun rays over a very small area, and we will see it through some animations in the subsequent discussion how the solar radiation is focused. And there are two ways to focus this solar radiation. One is called point concentrating. We focus all the solar radiation at a point, okay? And the second one is line concentrating. We focus the solar radiation over a line. And point concentrating are of two types: solar tower and parabolic dish. Line concentrating are of two types: parabolic trough and linear Fresnel reflector. So these four technologies, there are few more sub-classification of these technologies, but broadly there are these four: point concentrating two types, solar tower and parabolic dish; line concentrating of two types, parabolic trough and linear Fresnel reflector. So solar tower, we will see first here. The point concentrating technology, they are of two types. One, there is a receiver. In all the solar thermal technologies, we will when the sunlight comes, there would be one collector and then there would be one absorber. Okay, so these are two important components: collector and absorber. Absorber we also call receiver, absorber or receiver. Okay, so sunlight falls on the collector, get reflected or focused by a collector to the receiver, and receiver produces the desired heat. Okay, so in a surround field, the collectors are all around a receiver. This is the receiver or absorber. These are collectors. These are collectors. Okay, they are all around, and whereas the another type of, this is the second type, where we have got uh, collectors only on one side, only this side. There is no collector this side. Okay, only on one side, and the sunlight comes and gets focused on the receiver. Here the sunlight comes and get focused on the receiver from all around. Okay, but here the sunlight comes and get focused only on one side of the receiver, right? And we will see why we use this type of solar tower and when we do use this type of solar tower. So this is the surround field solar tower. Through an animation, I tried to explain. These are all the collectors. We call them heliostats. Heliostats means they are stationary, focusing the sunlight over the receiver. This is the receiver, and I'll see the flux distribution. This is how the flux distribution is obtained, and which is what this is how the heat is produced inside this receiver, and there is a working fluid flowing. Okay, so this heat is absorbed by this working fluid, which is then ultimately sent to the power plant for electricity production or for various other purposes. It need not be just a power plant. It could be a process industry. It could be um, um, metallurgical industry or some other industry where you need high temperatures. Then this is polar field, where the second type of solar tower, uh, where the field is, or the heliostats are only on one side. The collectors or heliostats are only on one side, and the sunlight comes and gets focused on the receiver. And this is the flux distribution. This is the flux distribution on the surface of the receiver, and this also, there is a working fluid flowing, and that working fluid takes the heat from this absorber or receiver and send it to the power plant for production of steam, and hence running the turbine. Okay. Now the question is, why there is only one side? So this type of field we use when we are away from the equator, right? So when we are away from the equator, say we are in the northern hemisphere, then we know that the sun rises in the east, sets in the west, and most of the time it remains on the south. So if you have got any uh, mirror or heliostats on this side, they won't be effectively utilized because they would be facing the back side of the sun. The sun will be facing their back side, which is a non-reflecting side. So there is no use of putting any heliostats this side. Therefore, the heliostats are only on this side. This way we save on uh, plant cost, and hence we try to reduce the cost of production of electricity. Then this is one of the line concentrating types I discussed initially. There are two types of concentrating technologies: point concentrating and line concentrating. This is a line concentrating one, where there is a parabola, and this parabola has been given shape, has been extruded. This we call parabolic trough. The sunlight falls on this parabolic trough, gets focused on the receiver, and there is a working fluid flowing. It's same as in the solar tower we saw, and this working fluid heats up and it produces, which is sent to various applications, either power plant, just like in the solar tower. And the flux distribution has been shown here, right? This is the flux distribution which has been shown here on the surface of the receiver, and there is a fluid flowing inside this tube. Usually this is tubular in shape, and say there is fluid flowing inside the tube to produce the necessary, to absorb the heat from this receiver and make use of it for various needs. Then the second, line concentrating type. So there it was a parabolic trough which was focusing all the solar radiation along a line. Here also we are focusing the solar radiation along a line, but here we have got flat mirrors. These are flat mirrors. All right, they are individually rotated, but they are rotated only in one axis direction. Okay, they are rotated like this as the sun moves from one location to another location. So we need to adjust the tilt of these mirrors so that they all the time focus the solar radiation on the absorber, because absorber is the place where the working fluid is flowing, which we have to heat up. Right? Now this is the point concentrating type again. The first point concentrating type was solar tower. This is the second point concentrating type. This is called parabolic dish. So in here we have got a parabolic dish. Okay, this sunlight falls on this parabolic dish. Okay, and it's getting focused at the absorber or at the receiver, and there are tubes here inside the receiver which through which working fluid is flowing, and you this way you take out the hot fluid which you can use for some other purposes, various other purposes. So here we have shown the heat flux distribution on the surface of the receiver. So these are all various technologies we discussed. Thank you.